Okay, good afternoon. Let's continue our discussion. So we were discussing about contrast stretching and the need of image enhancement or image processing or pre-processing in general for computer vision task or making better inference. So in that light, we have seen pre-processing through contrast stretching. Okay, so but the problem in general or in some scenarios is contrast stretching may not provide a very good solution. The reason is, see, if we have an image in this, say, assume that the intensities can range from 0 to 255. Okay, and there are some black spots. Okay, there are some black spots in the sense that their intensity is 0. Okay, and then there are some white pixels. Okay, and their intensities are 255. Very close to 255. In that case, so the remaining image is of low contrast. Some of the regions in image have 0 intensities. Some of the pixels in the image has very high intensities, close to 255. But however, the image is of low contrast. So what do we mean by that? Except, say, if I see the gray level distribution, so number of pixels having 0 and number of pixels having 255 and so on. Okay, and number of pixels having 210 and so on. All this is referred to as histogram. What is a histogram? It indicates the gray level distribution. Okay, of an image. Just if you want to have an example, we can have a 3x3 image. If we consider in this, so if we consider 1, 1, okay, 0, 0, 2, 2, 2, 3, 3. Okay, if we have a pixel values like this for a 3x3 image patch, then I want to know the gray level distribution in this. How many pixels have 0 intensity? How many pixel has intensity 1? How many have 2? And how many have 3? This distribution is referred to as histogram. Okay, so how many have zeros? The count wise, there is
2, sir. 2.
2. Oh, sorry. There are 2 pixels having intensity is 0. And then how many have 1?
Again 2, sir.
Again 2. And then how many have 2?
3, sir.
3. And then again 3?
No, sir, it will be 2.
2 only. Okay, sorry. And 2. See, given this is called as histogram. This essentially gives the frequency of pixels taking a particular intensity. Okay, so this can also be converted into the probability of a particular intensity occurring in an image. Okay, so if I consider in this image, what is the probability of having 0 intensity in this image? So if this is a 3x3 image, so total number of pixels here are 9 pixels. So if I want to convert this class, the pixel frequency or frequency plot of the intensities into the probabilities, what should I do? I can simply, if I want to convert this into the probabilities, so instead of frequency of taking a particular intensity value, this is intensity. Gray level value. Okay, and y-axis is what here? Whatever currently we have plotted.
Number of pixels.
Yeah, number of pixels are frequency. Okay, number of pixels at that intensity. Okay, or frequency, this can be referred to as. Okay, frequency of taking that particular value of intensity. We can consider this as the frequency. Okay, so if you want to convert this into probabilities, what should we do? If you want to convert into probability,
So we can divide the frequency by the total number of pixels.
that's all. Frequency we can divide by the total number of pixels. Okay, so essentially this becomes 2 by 9, all those things. Okay, this is again 2 by 9. Okay, and then this is 3 by 9. Okay, and then again 2 by 9 and so on. Okay, so this gives in terms of probabilities. Fine. So this gives essentially the intensity distribution of in an image or gray level distribution in an image. So if I consider L as the possible a gray level, so if I consider this with L, if I denote this with L, what we are getting in terms of the probabilities is P of L. P of L is essentially the frequency divided by the total number of pixels. Intensity distribution or probability. Occurring a particular gray level in that image. Okay, so usually this is considered to be an important information because this gives the gray level distribution of an image. Say it will tell if I see the histogram or the probability distribution. Okay, this can also be considered as the because it's a probability distribution, it is a kind of probability mass function for this intensity values. So this gives whether it is a dark image or whether it is a bright image or how the intensity values are distributed. So in this particular example, what we are saying, there are some pixels having the intensity values which are very dark, and there are some pixels having some bright, very bright, and remaining pixels have the intensities in the middle range. So their frequencies are something like this. Okay, so essentially, see, it need not be concentrated in all region, all gray levels as well. So it can also be, say, for example, it can be concentrated in some region of the intensity space. So intensities. This is again L, and this is considered as P of L if you convert into probabilities. Otherwise, frequency, class frequency, we can write. So we can give some notation even for that if required. Okay. So now if we have such an image wherein there are some dark pixels, some bright pixels, but remaining pixels are of low contrast. In the range, say, assume that these ranges is from say 150 pixels to 200. Okay, so in this range only, there are many of the intensities in that image lies. Okay, many pixels have the intensities in this range. However, if I apply contrast stretching here, do you think, do I gain any information more, or do we increase the contrast? Can we increase the contrast of this? Okay, such an image by contrast stretching. Yes or no? Does contrast stretching help in this case?
No, sir.
No. Answer is no. Okay, the reason is you anyway have minimum and maximum intensities and it doesn't help. Okay, so this stretching is happening just based on minimum and maximum intensity values. It is not based on the overall intensity distribution. So we should have some way or some method, okay, with which we can increase the overall intensity distribution itself. Say, since these intensities are concentrated in this range, I can somehow make it. Okay, so if I say I can retain this to be 0, some whatever pixel intensities at 255 to be at 255, assume that there are 5 here, there are 6 here. Okay, I can retain them. But remaining whichever 15, say 12 or whatever, these I can redistribute such that this is more spread over. Okay, well, it can be more spread over in the other region. Of intensities, so that what happens previously, which was there in 150 to 200, now I can make this to stretch over say 50 to 250. Is it not? In that case, I can have the better contrast or better visibility for the image. The method which doesn't only take the minimum and maximum intensities, okay, and linearly stretch it, rather it takes the whole intensity distribution and tries to map the intensity distribution itself to uniform distribution. That method is referred to as histogram equalization. I hope you understood what is histogram. In this discussion, it is the class frequency or intensity frequency plot or intensity probability plot. Okay. And equalization of histogram means we would like to stretch the histogram to close to a uniform histogram. So let's take a small example. See, let us take a small example and let's write there what is the histogram first. Okay, and after that, let us try to see if we wish to apply a histogram equalization. Okay, or if we want to improve the histogram plot to be having more contrast. Okay, how do we do that? So let the intensities be like this. So assume that if these are the intensities for a 3x3 patch, image patch, how many bits do you think are required to represent these intensities?
So
How many?
bits.
Two
So
bits.
2 bits.
2 bits. 2 bits are good enough. Okay, because 0 to 2 power 2 minus 1. That's good enough. Okay, now we just want to plot the histogram. Okay, so now how many zeros are there? 1 0 and then 2 ones, and how many twos? 3 twos, and so this 1 2 3. This is what? This is the class frequency plot. This is L intensities. We are denoting the intensities by L. Okay, original intensities. Okay, and then the class frequency plot. So I write here P of L. Okay. However, I have denoted only the intensity values here. Of course, we can also write 1 by 9, 2 by 9. So if you want to be more specific, 3 by 9 and 3 by 9. Okay, these are the class frequencies. So if I want L ranges from, L can take from, L is the intensity, original intensity. Why I am saying original intensity and so on? Because I want to apply some transformation to this. Okay, some equalization or contrast switching or whatever. After applying the transformation to this intensities L, okay, I will be getting modified intensities. Okay, so these modified intensities after my transformation are supposed to be distributed even better than the original distribution of the gray levels. Okay, that's what is the expectation. Okay, what is better in what sense? Having better visibility or better contrast. Okay, it's an enhancement pass. That's what we are thinking. M are modified intensities. So we will see later. Okay, will that improve or how much, how well does that improve and so on. So we will be getting M here. Okay, again, the intensities after transformation also will be 0 to 3 only in the range, but they get slightly redistributed. Okay, so we will see what transformation will make us better, and that we want to say it is guided by making the distribution more uniform. So this is the, if we say that this distribution is not still uniform, we would like to bring this distribution, okay, P of M now, okay, close to uniform distribution. Okay, what do we mean by uniform distribution? They are spread across all gray levels. They are not concentrated in only few gray levels. Okay, that's what we mean by uniform. Hope you understand the point.
Sir,
Yeah.
so that means that we are making all the original intensity levels as equiprobable.
We attempt to make it, or we try to make it, but the problem here is, see, this is not a continuous frequency, continuous intensities are not in the continuous line. Okay, so they are discrete. So you can't make an intensity one, some of the intensities in 2 to 1 and some of the intensities in 2 to 3. Okay, we can't reshuffle. We don't have that freedom. Whichever intensities all at 2 has to be together. Either they can be with small, slightly represented with small intensity value, lower intensity value, or higher intensity value, or with same intensity value. Okay, because I can't change the 2 pixels having same gray level to different gray levels. That's ruled out. So given that we will not get exactly uniform distribution, okay, we will only get approximately uniform. We will see what it is. Okay, we will also see with some images on what it does.
Okay, sir.
So essentially, just to give you an idea before I discuss. So if say if the class distribution is like this. Okay, if the intensities are like this, the class, I have not plotted the x-axis, but if this is like this, okay, and then this is P of L. If this is like this, what we wish to do essentially is, see if I make this transformation to this L and get the modified intensities, my modified intensities should be such that if I take any bin, okay, in that bin, the probability, if I count, okay, the sum of probability should be constant. It's like exactly in a continuous random variable. So how do we account if there is a continuous random variable and this is P of L or P of M, okay, then how do I assess what is the probability around a given value of L star? We take a small bin around this. Okay, in this bin delta L or whatever. Okay, so in this bin we will try to see what is the integral of the probabilities in that bin and assign that to P of L star. Okay, so P of L star ideally is 0. So what we do is P of L star, okay, is less than or equal to L star plus delta L. Okay, and then probability of L lying in the range from probability of L belonging to the range L star to L star plus delta L. Okay, or L star minus delta L to L star plus delta L. That's what we do, right? And then how do we get that value? We get that value by integration. Is it not? And in the similar manner, we want to do here also. Okay, so in a given range, we want to say that in this bin, whatever is the probability, okay, so that same probability value we want to get even in the other bin range, like that. Okay, so essentially, if I apply transformation, it should be like that. How it should be is, in wherever there is a small intensity, small frequencies, they will be spread out very closely. Wherever there are big frequencies having large number of pixels in that, they will have a more spacing with respect to the next intensities. So what will happen? They will get space like this. Okay, and again all these other small things will be together. Okay, and then the other intensity will be somewhere here. Okay, other intensity will be somewhere here. Okay, other all intensities will be here, and then it ends here. Okay, so it's like this. So essentially what I'm doing, if I see any bin there, if I count the overall say probability, then it will be roughly equal. That's what I will try to manage. Is the point clear?
Yes, sir.
Yeah. So we will see that now with this example. Okay, this is what is essentially done in histogram equalization. So we would like to have equal distribution in each bin. Okay, how big should the bin be? Okay, that depends upon the number of pixels I have, the intensity distribution we have originally, and many of those things. Okay, so you roughly, but you see that the spread now, wherever there is a high frequency, you will get like enough space to that, such that it can be very well distinguished from the other high frequency. Okay, pixels. So that the contrast will increase. The low frequency pixels, if there are very few pixels, so you can group them together, because they anyway doesn't make much difference. Okay, so in terms of visualization, that's how it happens through histogram equalization. Of course, histogram equalization is also a in enhancement technique. As we discussed sometime in the beginning, enhancement technique is to make the image prepared for subsequent higher level tasks, or to make it visually pleasing or visually better. Okay, so it may not yield in all cases a better result. So if my objective is to see very small details, sometimes they may get enhanced very well by histogram equalization, or sometimes even you may not get, they may not get enhanced as well. So the enhancement also need to be done at the application dependent way, in the application dependent way. This is not a restoration. As I mentioned, restoration means if we have a forward process, what has happened, we want to do undo the process. That is restoration. Okay, so this is still a heuristic kind of thing in some sense, but it's a kind of intuitive to adjust the gray levels in a uniform way in a bin, so that you can visualize all intensities, okay, at this different bins. Okay, that's the idea. So now let's take this example. So we have actually the probability distribution of this. So I will again take the same example. See, what we want to do, we want to map this distribution to a uniform distribution. So let's take this. Okay, so we have seen that P of 0, L indicates what? L indicates original intensity. Okay, M is modified intensity or equalized. Okay, so we have seen the PDF of the intensity values. L equal to 0 here, L equal to 1, L equal to 2, and L can take 3. Okay, of course, M can also take these values. P of 1, P of 2, and P of 3. We have seen these values as what? 1, 2. P of 1, 2, 3, and 3. Now, what we do in terms of C, as I mentioned, we want to see that equally distributed, okay, in each bin. So to see that, what we need is a cumulative distribution function, because we see in that bin the sum is equal. So to see that the sum of probabilities, if we want to get hold of, we need to calculate the cumulative distribution function. So let's calculate the cumulative distribution function. How do we calculate? For L. Okay, so if we consider it as C of L, okay, then we want to write it here itself to make it easy. C of 0 is how much? C of 1. I suggest you people quickly tell the values. C of 0 is 1 by 9. C of 1 is
3 by 9.
3 by 9. And C of 2 is
6 by 9.
C of 3 is anyway 1.
1.
Okay, good. So now what is the idea? The modified intensities should be such that, okay, so they are proportional to the cumulative distribution, because they get placed in such a way that they are equally distributed in a bin. So how do we decide a modified distribution is kth intensity Okay, if we consider it as say L naught, okay, I just have written here L equal to 0 is L naught, L1, okay, L2 and L3. Okay, so and then the modified intensities are M naught, M1, M2 and M3. So so what we are trying to see is the mapping between the original intensities to the modified intensities. How do we map? The mapping is done through the cumulative distribution of the original intensities. Okay, such that the MKs are now replaced or placed in such a way that they have the distribution proportional to the cumulative distribution of the original intensities. Okay, so based on that, now if you want to decide, so but these are the intensities we want to have. This is only probability. So if you want to get this MK, how do we get this? The original intensity multiplied by the cumulative distribution. This is proportional to the cumulative distribution. That's what we wanted to do. Okay, so the original intensities gets multiplied by the cumulative distribution to get the current intensities. But usually the intensity values are only discrete, as you know. So because pixel intensities we usually represent and they are with integers. So we need to apply an rounding operation or some operation to bring them to integers. Okay, so this expression enables us to get the intensities transformation. So essentially this is the transformation expression. MK is somehow transformed from LK. What is this transformation is doing? It is essentially bringing the intensities of MK proportional to the cumulative distribution of LK. That's all. Okay, multiplied by the LK because we want to see that the monotonicity is maintained and that gets weighted by the cumulative distribution. Okay, so now if we apply this, what is M naught or the first intensity? Okay, so 0 L equal to 0 gets transformed to M equal to what is the question. Okay, so L naught is equal to 0 means that M naught equal to how much? Okay, so that means all the pixels having intensity of 0 here, will they get, where do they get placed is a question. Okay, all the intensities having 2 here, where do they get placed? All the intensities having 3 here, where do they get placed? Similarly, 3 here, where do they get placed? That's the questions. These are the questions. Okay, so L equal to 0 or L not equal to 0, either you can take. So for better understanding, I have put MK here, but M can take a variable values. So you need not put the index in that case. So if you understand that M is a variable, it can take 0 to 3. You need not put a subscript there. Okay, it's up to us. So we can remove the subscript and then say that the M takes different values. Okay, just to make that highlighted, I have put this subscript here. Okay, let's put the subscript also just to highlight. But you know that L takes 0, 1 and so on subsequently, and we want to see what the corresponding M is. Okay, so then M not equal to how much? So round, I will just say, so how do we represent like this? Okay, so we represent round operation by this. I think seal and floor, you know, I think how they usually are represented. Round, let's put like this. So then how much? 0 into LK into, you can take LK into C of LK or C of LK into LK. It's up to us. 1 by 9 into 0. How much is this? M not equal to how much?
0.
0. That means L equal to 0 imply that M equal to 0 after transformation. That means all the 0 pixels here gets mapped to what? All the 0 pixel here gets mapped to 0. M equal to 0, 1, 2, and 3. Okay. So now let us take L equal to 1 case. M equal to how much? Okay. So how much is this? 1 by 9 or 3 by 9? It's 3 by 9 into 1. And then this is the round operation. This is equal to how much? Round operation of 3 by 9.
0.
0 again. So what does it mean? So even the intensity is having L equal to 1 are also mapped to L equal to 0. So here 1 plus 2, this is 3. Height of this is 3. That means the M1 is also equal to M0 in sense that, of course, so this notation now is little confusing now. So L equal to 1 also gets mapped to M equal to 0. Okay, so let's drop this only here. Let's put the K. Of course, otherwise let's leave the K everywhere. We hope that we know the range, what L and M take. Okay. Fine. Okay. Fine. Let's complete this. Let's complete the other values. L equal to now 2 implies M equal to how much? How much? 6/9 into 2, and that is equal to round operation. How much is this? L equal to 3. L equal to 2 is how much? Somebody can tell quickly.
So 1.
Yes, it is 1. So it gets mapped to 1. So what does it mean? The intensity of all pixels having this intensity, if you want to denote with other sketch, we can color, we can do that. So all intensities which were at 1 now, which were at 2, L equal to 2, now gets mapped to intensity 1. Okay. Okay, so L equal to 3 implies L equal to M equal to
3.
3. Very good. So they get these are still here. Okay. So this is what is the modified intensities. Now this is the original image. Okay. So what is the modified say the histogram equalized image? How does it look like now? How does it look like? So wherever you have 0, there still 0 is there. Wherever 1 is there, what intensity you have to put? What is the modified intensity?
So 0.
0. Okay, wherever 2 is there, we have to put what?
1.
Okay, wherever 3 is there, 3 times with 3. Okay, so this is supposed to be a better contrast image than this. This here we can visualize much more clearly the uniform distribution nature of this compared to here. Okay. In the small examples, it is very difficult to see, but when there are large number of pixels, you can see that the distribution gets more or less uniform or spread uniformly across different bits. See, for example, for the same example, this is histogram equalization. What it did essentially, because there is a see 0 intensities, 1 intensity, 2 intensity, for all intensities are there. Okay, the transition between the intensities is very small from one gray level to other gray level. We have a difficulty, or the eyes has visualization of different gray levels is difficult. So what this has done is, it has grouped the intensities which are very of small frequencies together, and then it has separated well the frequencies which are like of high frequencies. Okay, so that's what is being done by this histogram equalization. Okay, so if I apply contrast stretching here for this, what do you think will happen? So instead of histogram equalization, assume that we have applied contrast stretching. Okay, what do you think will happen? Any answer? What do you think will happen if I apply contrast stretching to this?
It will remain same.
It remains same. That's all. Nothing, no change will happen, because there is a L minimum is same as the capital L minimum. L maximum is same as capital L maximum. We have the lowest and highest intensities already in the image, so it doesn't change anything. Hope you understand about how we perform the histogram equalization. This is very important operation, usually considered as one of the very prominent operation of image enhancement. Okay, this gives us a flexibility of enhancing the details of image in a better way.
Sir,
Yeah.
so for rounding off, we use the floor function over here.
No, not floor. I have just put round itself here.
Okay.
But we can consistently use one of them. There is no.
Okay, so the choice of using either floor or ceiling function is arbitrary.
Yes. But we should consistently use it. So in the sense that for some pixels you floor it and some pixels you seal it. In that's not a good strategy.
Okay, understood.
Yeah, good. So any other questions? So otherwise, what I plan to do now is to flash some of the slides from the Gonzalez and Woods book, which will have a good understanding of what we are discussing, which will give a better understanding of what we are discussing from the visualization perspective. Okay, so what I do is I will quickly move on over the slides. Wherever we need the discussion, it's up to you to stop me. Okay, so as I mentioned, these slides are from the Gonzalez and Woods book. So they have provided with the request these slides as well for any. Okay, so as I mentioned, the definitions are all discussed before. So I will not discuss too much on them again. So enhancement is to make them visualize better. Restoration is to do inverse of the degradation process. Here you can see an advantage of image enhancement in medical image, in any medical image, where actually all these nerves are very small ventricles are nerves. So these are very well visible here after enhancement. Okay, so the same is here. This is a restoration example. When a car is moving or a person is moving, if we image it, what will happen? There is a smear that happens in an image because of the averaging process in image formation during the exposure time. So that is referred to as blur. And how do we do restore from blur is a good important problem. We will see that later. So I will skip the slides, which are not very important. Only for visualization, we can use the discussion. So this image shows different operations, arithmetic operations on an image. Just like we perform on a on numbers, we can also perform the image matrix, some of the arithmetic operations on the image matrix to enhance it. So if this is the original image, if we apply, for example, any thresholding, we may get say some thresholded image. If we apply some kind of we will see how to get edge map later. Okay, some kind of filtering will give this. If we add some value, it will increase the brightness. Okay, if we increase too much, if we add too much higher value, it will saturate the image content. So that means most of the pixels will become 255. Only few are less than 255. So that is referred to as saturation. So we can also apply in some cases thresholding. Thresholding meaning all pixels greater than some threshold are put to 1. All pixels less than some threshold to 0 to binarize the image. That may highlight some of the regions, important regions in some cases. But we will see that in more detail. So what's the, how can we binarize an image in a better way? This is also one kind of arithmetic operation on images. Other is on the, this is also, they have created a mask and then subtracted this mask from this. Okay, so if we have any constant background with which we are taking images and we want to get away from that background illumination, one way is to subtract it. Of course, there are other ways in which we can also divide with that corresponding intensity variations. So to highlight the intensity variations also, we can use the subtraction of the image matrix 1 to image matrix 2. So this we have seen. So what's the, you can enhance by adding, or you can bring a brighter image by adding a constant, or you can multiply by a constant. So another arithmetic operation is, if you give RGB image, you can average RGB channels to get grayscale image. There are different ways of weighted sum of RGB channels to get into better grayscale image. So there are some applications where the instrument or sensor itself will bring in some kind of degradation in image formation. So that is usually referred to as gamma correction to improve with such degradations. So most of the image formation happens with a power law relation with respect to the actual radiance intensity values. Whatever we get is this, and the actual radiance is this. So gamma value is fixed for an instant for a sensor. So how do we use that gamma value and correct or improve? That's also one more way of looking at. So this is another example where we can see that if you want to highlight the other regions, black regions rather than white regions, so image subtraction can be used. So of course, this is also used in document. Image subtraction is also used in document analysis, because when we want to print with white background rather than black background. So this is, as I mentioned, this is the power law correction. So where the image is formed with some gamma, and that can be corrected through the transformation equation we have. So these are not intensity transformations, are the contrast stretching or histogram based transformations. These are with more like arithmetic operations, either direct arithmetic operations or nonlinear operations on image matrices. So this is actually looking at the image at different bits. As we have 8 bits in an image, what information does the most significant bit gives? What information does the least significant bit gives? Such things also can be analyzed to make use of it for better transmission or other image operations. So essentially what people do is, because highest significant bits are important, they will put together a couple of highest significant bits and transmit. And at the receiver, even with this, we can reconstruct putting all these values as zeros, because they're quite random or small. So this is an example of thresholding. As you can see, they have put a threshold of 100 here, and the high intensity, what we want to capture is this black intensities, or the white intensities are all background. So by putting the threshold and then bringing all the zeros to the black and then remaining all to the white. So it's a good binarization by thresholding. And so this is contrast stretching that we were discussing. As you can see here, this is the original image. Okay, so and they wanted to highlight these regions in an image. So they have roughly the low intensity region and high intensity region is made with very small slope to the mapping to the other gray levels, or the transformation is done with mapping the original intensities to the output intensities with a very low contrast in the small intensity, low and bright intensity regions, and the mid-level intensity regions are all well stretched to get the better contrast. As you can see, the information is in the gray level, that means during the mid-range of intensities. So this is what is the contrast enhanced image with this input-output mapping. Hope you understand this based on the discussion that we had. So these are the histograms. So this is a dark image. As you can see, the histograms clearly shows that the intensities are spread over the low intensity values. This is a bright image showing that the intensities are spread over the high intensity values. And then this is in the mid range but low contrast image. This is a better contrast image. This is just to get a better idea on what the histogram gives, information gives. This is the discussion that we had. This is a similar example they have taken, and they wanted to see the equalization of this image through histogram equalization. So probability distribution function we have calculated here with the for each intensity, and then cumulative distribution function, and after that using those to map onto the equalized image. So this is the original histogram. This is the equalized histogram. Okay, and in the original image, putting these pixels in place of these pixels at the original, at those respective locations, will give this. Hope this example is clear on histogram equalization. This is also another example where the histogram equalization is useful, where even if we have the low contrast image or high, like the image at bright region with low contrast or dark region with low contrast or whatever. So in general, it is more powerful than the contrast stretching, because in contrast stretching, you need to identify in which region of intensities you need to stretch it to visualize the image better. Whereas in histogram equalization, we are identifying, we are finding out the histogram and we are trying to map it roughly uniformly, okay, in the discrete scale with histogram equalization. So as you can see here, this is original histogram, and this is the equalized histogram. You can see, if you see any bin, if you counted the number of pixels in that bin, okay, you can see that they are roughly adds to the same value. So this is another example for histogram equalization. Okay, so I will probably stop with this these examples. So I would suggest that if you have any questions, you can ask. So what this example shows? What this example shows, can some of you tell?
Contrast stretching.
Contrast stretching, but I wanted to demonstrate or convey something from this image.
Linear stretch.
Yeah, linear stretch, fine. Okay, by looking at this, can you tell? Contrast stretching versus histogram equalization. If you see what's happening here, this is original image. Contrast stretching has given this, whereas it has linearly stretched, and this is the equalized image, where you can see that, okay, the intensity distribution here is much better than this. Okay, so essentially, histogram equalization takes care of whole intensity distribution, try to map to uniform distribution, whereas contrast stretching is trying to take only minimum and maximum and stretches it. So when we have the intensities in bright and dark regions and the remaining intensity somewhere in the middle, okay, histogram equalization is preferred compared to contrast stretching. Okay, so any questions so far on this? Okay, so if you have no questions, then we'll conclude here. In the next class, I will discuss on filtering, essentially where all it is needed and what is filtering, convolution and correlation, filtering through convolution and correlation. Okay, thank you then.